All right, so this is the solution to challenge problem number 1. Number 1 implying that there are more to come. Hope you at least tried it. It's a good problem. So I told you that you had this compound that contained an unknown metal combined with oxygen, and when you heated it up, I gave you different percents oxygen in the compound. The first thing I asked you to do was to calculate the mass of oxygen for every 1 gram of metal in the compound. What this problem is based on mostly is the law of multiple proportions. So, and which this is what you do in the law of multiple proportions. So I'm just kind of getting you started here. So because it's 13.38% oxygen by mass, we know that the difference between 100 and 13.38 or 86.68 is the percent mass that's the metal. Okay, so 100 minus this gives us 86.68. So in every 100 grams of the compound, we have 13.38 grams of oxygen and 86.62 grams of the metal. So we just do this division, we get the grams of oxygen per 1 gram of the metal. Doing the same thing for the second compound after we've heated it up and driven some of the oxygen off. It was 9.334 mass percent oxygen, so 100 minus 9.334 is 90.666. And so we say, okay, let's assume we have exactly 100 grams of the compound, then we have this many grams of oxygen, this many grams of the metal. Doing the division gives us the grams of oxygen in the second compound for 1 gram of the metal. And the same thing for the third. After we heat it up farther, there's only 7.168% oxygen by mass left, so assuming 100 grams exactly of the sample, we have 7.168 grams of oxygen, and 100 minus 7.168, which is 92.832 grams of the metal. Doing the division, and we get this many grams of oxygen per 1 gram of the metal in the third compound. So that's part A. Part B. This is, again, law of multiple proportions. So what we do is, now that we've gotten to the point where we have the grams of oxygen per 1 gram of the metal in all 3 compounds, from this point on, the amount of metal stays the same in all of the compounds, and that's important for us. So for every 1 gram of the metal, we have this many grams of oxygen in compound 1, this many grams of oxygen in compound 2. Now, my subscripts here, please don't let them confuse you. It doesn't mean O2, 2 atoms of oxygen, or 3 atoms of oxygen. The subscripts here mean compound 1, compound 2, and compound 3, okay? Just to keep them straight, because labeling is really important in this problem. So if we divide the grams of oxygen in compound 1 by the grams of oxygen in compound 2, we get 1.5 to 1. Same thing with the grams of oxygen in compound 1 to the grams of oxygen in compound 3. We get 2 oxygens in 1 to 1 in 3. Now, notice I have grams here and I don't here. That's because now that we have this, sure, there are 1.5 grams of oxygen in compound 1 per 1 gram of oxygen in compound 2, but because it's the same element which has the same mass, we also know that there are this many atoms of oxygen in compound 1 for 1 atom of oxygen in 2, and the same down here. So now we know for every 1 atom in compound, 1 atom of oxygen in compound 2, we have 1.5 or 1.5 gram atoms of oxygen in compound 1, and 2 and 1 for every 1 in 3. All right, now that we know that, what we can do is, okay, this was from the previous screen, right? We found that there were 1.5 atoms of oxygen in compound 1 for every 1 atom of oxygen in compound 2. Right here. So I'm just flipping it upside down. And we also know, because in the problem I said, let's assume, we have to assume something. I say we're given that the formula for compound 1 is MO2, right? Which means there's 1 atom of M, the metal, for every 2 atoms of oxygen in compound 1. So if we just do the atoms of oxygen in compound 2 per the atoms of oxygen in compound 1 times 2 oxygens in 1 for every 1 metal. Remember, metal stays the same for all the compounds now. So it doesn't matter if it's 1, 2, or 3. It's the same amount of metal. We have 1.333 atoms of oxygen in compound 2 for every atom of metal, because you see the units here cancel. But in the case of the law of multiple proportions, says that this should be a simple whole number ratio. And so it is. If we multiply this by 3 over 3, we get 4 atoms of oxygen in compound 2 for every 3 atoms of oxygen, 3 atoms of metal in compound 2. And so we get M3O4 is the formula for the second compound. Now doing the same for the third compound, we found previously that there are 2 atoms of oxygen in compound 1 for every 1 atom of oxygen in compound 3. Flipping that upside down, multiplying times 2 atoms of oxygen in compound 1 for every 1 metal in compound 1, or in any compound, we get that there's 1 atom of oxygen in compound 3 for every 1 atom of metal, because these cancel. And so that means that the formula for the third compound is MO. Now, part C, we want to find the name of the metal, the identity. To do that, if we can find the molar mass, then we can look it up on the periodic table. So I picked the numbers from the first compound. You can pick any of the compounds and it works just as well. So I found in the first compound we found there are this many grams of oxygen. So I divide that by the molar mass of oxygen. That's this number right here. I read this from the periodic table, and it gave me this many moles of oxygen in the first compound. Now we know that there's 1 mole of metal for every 2 moles of oxygen in compound 1, because we were given the formula. So multiplying here, we get this many moles of metal in the compound 1 for 1 gram total. So if we have 1 gram, for 1 gram of the metal. For 1 gram of the metal, okay, so we have the mass divided by the moles, grams over moles, gives us the molar mass, 207.1 grams per mole. The closest to that is lead, so we know that the metal is lead. One real quick point before we wrap up here. Back here, and even back here, you could have flipped any of these upside down and you would still get the whole ratio. Well, here you have to do it this way to get the 1 gram of metal on the bottom, because that's what we asked for. But here, I can flip these upside down, and it's just you'll get numbers less than 1, and I prefer numbers greater than 1. But it would have worked either way.